to like repeat it just for the sake of it. It's less natural then. It won't come off right. So I'll probably say something else awesome. We talked about binary trees last time, right?
Just tell the same story to another class.
But make sure I'm recording it.
Tier 200 class. Yeah, with 200 class.
Well, that's where they mostly got the sound bites.
Yeah, I know.
Do you still have Whitman soundtrack?
So they're already tainted.
What do you mean?
I mean, they're a year behind you, and they've already been tainted.
I don't have the.
It's a preparatory course for Lippmann.
It's equivalent to CSC 150, but for Lippmann classes.
I have to look around because where the sound files are located inside the app, but they're in there.
Okay, then I'll look.
All right, binary trees. Okay, so I want to revisit these because we kind of covered it that very last day, and did I cover that a binary tree is a tree of trees, or did I not cover that punchline?
No.
Okay, good. So that means I wrote this the bad way then, right? We have duplication of code, don't we? Oh, that's right. I wanted to get the visits in. That's what. Okay, so add node. So we look at this code right here. So binary tree, everything to the left of a node is less than or equal to it. Everything to the right of the node is greater than it, right? So look at this code right here. Basically asks the question, right? Is the dude I'm adding, should it go to the left or to the right? Okay, and then it either adds it directly or passes the buck. That makes sense? All right, so everybody's read this code? We see it? So now I'm going to go back to binary tree. Oh, hold on. I'm in the wrong class there. You're going to still see that code. So it's still legit. It's still legit. They're just a little ahead of you. All right, so here's our node, add child. Should it go left or right? Pretty much what we just looked at, right? Okay. Now I go to binary tree. You see how add effectively repeats that logic? Now, right off the bat, does that sound like it's probably the red flags should be going off, right? I have the same logic in two places. Why? Well, in this case, we are thinking about our binary tree as kind of the basket that's holding our nodes that are linked together in this special way, right? Whereas from a node perspective, we're thinking about our node as the link in the chain. That it has up to two things hanging off, right? Okay. So in our mind, we're thinking of these guys as being separate entities. In fact, we're programming it such that they're separate entities. Correct? Okay, so let's go back to our picture. All right, so let me, so here's all right, so a binary tree has a value and up to two children. Let's accept that as a starting point. So I'm gonna, let's see, what did I say here? Nonlinear linked data structure, nodes to the left, nodes to the right. Every node has at least two children, blah, blah, blah. All right, so we're going to say binary tree 2.0. It's 3 decimal places, significant digits, the thing. All right, so the previous definition is not inaccurate. It's just too specific. What we're going to say here is a binary tree is a collection of 0 or more binary trees. Where a binary tree has a payload and at most 2 child trees. All right, so I've kind of upgraded. Instead of calling them nodes, I'm calling them trees. All right, so everybody good with the words right now? I'm gonna explain the same thing in pictures. Okay, so I've removed the idea of a node here. Now everything's a tree. If we look at this guy, is that guy a tree? He has a payload. He has at most 2 child. I'm calling them trees. That means that this guy must be a tree. Is this guy a tree? Well, he has a payload. He has at most 2 child trees. Is this guy a tree? He has a payload. He has at most 2 child trees. In this case, he has 0. He has 0 child trees. That make sense? All right, so we can implement binary trees. We can think about binary trees as a linear linked data structure. Non-linear linked data structure where the linked values are binary trees, not nodes. All right, so what we're going to do is we're actually going to rewrite our binary tree in this way, and we're going to see how it simplifies it. Okay? But I'm going to leave the other code in place. Now, this is subtle. So if you're not quite following this yet, that's okay. This isn't like a deal breaker. All I've done is I've said, you know what, before we had this binary tree, and we had this thing called the node, and we treated them as completely separate things. But you know what? Kind of the same thing. Okay, they're the same thing. Now, if we wanted to wrap the top level, we could. That's kind of what we've done currently, where we essentially have a collection of nodes. So instead of calling them binary trees, we've called them nodes, where a binary tree is a collection of these nodes. That's okay, just it sounds less cool when you call them nodes instead of binary trees. And what is the top level binary tree? If I take all of this and I just throw it in a garbage bag, so that's labeled binary tree, what is that really? It's the dude who keeps track of the top level root node. Mm-hmm. That's what a binary tree would be. All right, but we're going to go back. We're going to implement this a second time, but we're going to use a little bit different naming conventions. And hopefully we see that it becomes even simpler. All right, so we're going to go in here. So we're going to say, we're going to create a Java class here called binary tree binary tree 2, our second version of a binary tree.
Yeah.
We're good with that?
Yeah.
All right. So we have our second version of a binary tree. And a binary tree, we said, if we go back to this guy here, we said this guy has a, where's my definition? You okay? Huh?
Oh, yes. What? Oh, my goodness. I'm just saying it's a payload.
It's what?
Payload? You asking?
All right, so binary tree 2.0 is a collection of 0 or more binary trees where a binary tree is a payload and at most 2 child trees. Okay, so we're going to have what I've been using this phrase recently called pseudo-recursion, right? Pseudo-recursion, where we have something that is of the same type. When we say regular recursion, we say it's a function that calls itself from within itself. Mm-hmm. Okay? what we've been doing a lot lately is we've been calling a function that is a clone of itself. It's a function that's owned by another dude that it's the same function, but it's a different instance of that function. Make sense? All right. So for my binary tree here, binary tree 2, we're going to say this guy has a payload. And right now we've been storing integers, right? So we'll store an integer. We'll say private int payload. All right. Then he's going to have at most 2 child trees. So we'll say private binary tree 2 left, private binary tree 2, whoop, right. So he's going to keep track of 2 instances of things that are like him inside of himself. So we'll have our constructor for this, public binary tree 2. Okay, this guy will take in a payload. All right, and we'll go ahead and set the payload. This dot payload is equal to payload. And when a binary tree is first born, we're going to say that it has 0 children. So this dot left is equal to null. This dot right is equal to null. All right, make sense? Now, here's where the magic comes in. Right now, I'm going to purposely leave off the visit in order stuff. Let's just keep it at the data structure side of things. So we want to think about adding a value to a binary tree. What does adding a value to a binary tree mean? So we're going to have public void add int payload. Okay, so we know we can't add it to ourselves. We already have a payload. We can't exist unless somebody gave us a payload. So we're trying to place this guy either to our left or to our right. All right, so we want to ask the question, where should he be? If payload, remember the most local definition of payload, all right, so this guy right here, is less than this dot payload. Now, if we wanted to give it a little bit stronger naming convention, instead of calling this guy payload right here, we can call this maybe like payload to add, something like that. And that way this question here reads a little bit better, where we can say if the payload we are trying to add is less than our payload. Okay, and really we're asking if it's less than or equal to our payload. Then we're going to add to the left. Else, we're going to add to the right. Okay? We have 2 options. We can either make this guy become our left child if we don't already have one. So if this dot left is equal to null, if I do not already have a left child, this dot left is equal to a new binary tree 2, passing it payload to add. I'll build a brand new binary tree and hang it off my left branch. Make sense? Else, this dot left dot add payload add. If I don't have a left child, I'll go ahead and build one and add them. If I do have a left child, I'll go ahead and ask my left child to add this guy. This is kind of the pseudo recursion. So we kind of have 2, this would be our real pseudo recursion here, where we're actually calling the add function from within the add function. It's just a different dude's add function. Okay? Whereas up here, I would still throw this into the category of pseudo-recursion-y type stuff where we're defining a let me give you a little more general definition of recursion. So up to this point, if we think about recursion, kind of our version 1.0 of recursion definition is a function that calls itself from within itself. Okay? But if we're going to upgrade that a little bit, and it's not even upgrading it, it's making it more general. Similar to what we're doing with binary tree here. So we're kind of doing this twice. So we're going to call this guy, I'm going to call it an object or function that is defined in terms of itself. So instead of specifically saying it calls itself, we're going to say that it's an entity. It's a programmatic entity that is defined in terms of itself. I like that. A programmatic entity that is defined in terms of itself. Okay? It's a pretty vague definition, and you're probably not going to necessarily find that written in some textbook, although it should be. Programmatic entity is awesome. Brought to you by Nabisco. Okay. But I think it's pretty accurate. Now, this kind of falls into the category of vocabulary versus conceptual knowledge. It's important you understand this conceptual knowledge that recursive type stuff, I've been calling it like pseudo-recursion, things like that, are functions that are things that are defined in terms of themselves. Okay, that could be a function call, that could be, in this case here, we're having binary trees being defined in terms of binary trees. So what's a binary tree 2? Well, it's a payload plus 2 other binary tree 2s. Well, what's each of those? Well, it's a payload plus 2 other binary tree 2s. What's each of those? It's a payload plus 2 other binary tree 2s. Okay, so we kind of have like this recursive type of, I don't know, move there, even though these are physically different objects. Where true recursion, from a language implementation perspective. So when you take the 470 class, which that's offered in the fall, you should all take that class. Fit it in your schedule. You can take it online if you have a scheduling conflict. But that class complements the things we do in here very well from the perspective of, in here you're doing applied, right? You're seeing, how do I use a language to solve problems? In there we look at how do you build a language. And the dots that get connected are, for instance, like right now, I'm saying the way that recursion is implemented in a programming language effectively defines recursion for you. You don't need words to define it. Okay, recursion says I'm going to have a variable environment that's going to have multiple little, boxes with on-hold functions that are stored for a later point in time. So recursion implementation in programming languages is defined in terms of a function that calls itself from within itself, its actual self. Not that's the pseudo-recursion that kind of looks like recursion in disguise or something like that. All right, so factorial, we've talked, that's kind of your introductory recursive function, like 5 factorial is 5 times 4 times 3 times 2 times 1, which means that 5 factorial is 5 times 4 factorial. 4 factorial is 4 times 3 factorial, so on and so forth. Each time we call factorial again, we're putting the current call on hold. And what that effectively has us do, this is language implementation, is we kind of like box up the current function, like to be continued. Okay, I don't know if you're playing playing chess or something like that, and you don't have time to finish the game. You have to like protect it somehow so you can come back and finish it later. But you might go start another game with somebody else. Let's just call that a close enough example. So we're going to box up this unfinished function for now, and we're going to push it onto, what kind of thing do we push things onto? Stacks. We're going to push it onto a stack. Okay, so recursion is implemented in terms of the stack data structure when you're building a programming language. In fact, it's also true that any function that you could write recursively, you could also write iteratively with a stack by effectively implementing your own recursion, building it into the logic. All right, but the 470 class is if you feel that programming is of interest to you. I know there's a love-hate relationship with programming, but for those of you who are computer science majors, pretty strong possibility you're going to end up getting a job writing software, whether you like it or not. So eventually you're going to like it. That class connects those dots for you. So you go from being a practitioner of something that you mildly understand, let's say, to understanding what's happening actually under the hood. So that when you make decisions in the language, you can think, oh, I wonder how this works. This programming language has implemented this one of two ways. Let's find out which of the two ways it's done it, and that tells me how I need to solve the problem. Okay, so it's a good class. You should. It's also probably our hardest class, but but it is fun. Yeah. So, I mean, it falls into that category of a class that, and actually all the assignments, the real frustrating thing in there is we use a functional programming language in the class called Scheme. I actually have a quote from a student from several years ago who was in the class, and students like, well, why am I using this? I'll never use this. He went and got a job for like 140 grand a year doing Scheme programming. But what's the reason I use Scheme is Scheme is a language that's a superset of another language called Lisp, which was originally like an artificial intelligence language. But it's a functional language similar to how many of you have used like a Texas Instruments graphing calculator or something like that, and maybe written a little program or something for it. You can program on them. That's a functional language. So very, very small language. You have a collection of like 30 things it knows how to do, and you accomplish stuff by linking multiple things together through functions. Well, the reason we use a simplified language in that class is because we're using that to build a language, and we don't want the two languages to be conflicting with each other. But at first, conflicting with each other in your mind. But at first, a functional programming paradigm is so different that you're going to feel like you're learning Scheme. Okay, but then all of a sudden, you're going to realize that, oh, I'm building a language like I've been using all along, building a Java-like language, something like that, using this tool that I don't really see a practical use for, Scheme, something like that. And by the way, I've been doing recursion left and right because it doesn't support loops, and I forgot that I didn't like recursion.
So that is the course that you built.
Yeah, 470. So, and it's only offered every 2 years. So your opportunity is to take it next fall. Not, you would rather take it you're going to be juniors, right? Yeah, so your opportunity is to take it next fall. Otherwise, you could take it during your senior year as an online course, but then you're butting that up against senior seminar, which is another monster type course. So you want to take it live, even if it's a scheduling conflict and you have to watch the videos or something like that. We can work that out, but okay. So understand here that we have a couple of different layers of recursive-like activities kind of happening. Okay. It doesn't matter what we call it. The vocabulary of it isn't all that important. It's just that we understand kind of what's going on. All right. So when we add something to a binary tree, we decide if it's going to go to our left, we either directly add it or we ask our left guy to deal with it. Otherwise, we're adding it to the right. If this dot right is equal to null, then we'll say this dot right is equal to a new binary tree 2, payload to add. Else, this dot right must be a real thing, And we'll just pass that payload on. Okay, so that's what add looks like for a binary tree. Come back out here to our main activity. Didn't we test this guy somewhere?
I don't think we had time to.
Oh, that's right. I just said, this works, trust me.
Yeah.
You probably did. See, take 470 and then you could do the same thing. Then you won't have to, it seems like a magic trick, but it's not. When I took a course like that, that was kind of a turning point for me when you start understanding the structures that are going on underneath and you become interested in those things. All right, so I'm going to go ahead. I'm going to build a binary tree 2. And we'll call this guy BT. This is going to be a new binary tree 2. And I'm going to go ahead and pass it my root node. All right, so we're going to attempt to build this tree here. So I'll pass it the 5. All right. That makes sense? Now, I'm going to say bt.add, and I'll add the 3. We'll add another 3. 8, 6. 8, 6, 5, 6. Eight, 3, 3. I'm just mimicking the tree we 833. Yeah, this is not even an accurate tree.
Yeah.
That's not an accurate. Well, actually,
That was a pre-order,
I think you're-
post-order or something.
okay, yeah.
The only thing we have that because
5,
So we can have it in there.
8, 6, 5, 6, 8. Oh, so this is really my tree up top here.
Yeah.
So 8 and the 6. Well, it doesn't matter. That tree we were just building would have worked. It just wouldn't have mimicked the tree we had. It'll put the stuff wherever they're supposed to end up landing. Okay. So that is my binary tree 2. Go ahead and run this. Make sure it doesn't crash on me. We won't see any output. We'll give ourselves output by doing the visit in order stuff.
Mhm.
Oh yeah, I'm on FalconNet now. Schrammel told me my account wasn't locked, so maybe it was just doing something funky.
And then Josh thinks it was locked, but then Matt locked it.
Oh, okay. Oh, so you have my back too.
Yeah,
Start for the day.
it's just the group chat.
Hey, still counts. Just using the resources around you. That's problem solving, right? Yeah. So then your next step is to find out why does that keep happening. Because it seems like about every 2 weeks, every 3 weeks, my account just randomly gets locked. Now, I do travel a lot, so I wonder if, and I'm always traveling with this machine, so I wonder if I'm checking my email from like a strange location,
Mhm.
and then coming back, I wonder if there's like just a security measure that flags it. But yeah, I don't know. I mean, better safe than sorry. It just seemed where it's more inconvenient is when I can't log into Blackboard. Something like that. But you know, the FalconNet life goes on. It's not that great to begin with. Okay, so is this thing? It's not running. Let me make it run now. Hmm.
I just heard Dr. Locklear.
Well, I just saw Professor Locklear run by. I haven't seen Dr. Locklear yet today. But he'll be at Bible study. I'll show
He
him
was
my.
in chapel this morning.
Yeah, I just haven't seen him as I was hobbling in.
I'd like grab you a can or something real quick.
To be honest, I actually went to Mexican Walmart the next morning, thinking a cane would help, and it wasn't going to help. So I walked all the way into the very back of the place at Mexican Walmart. And
What's it called?
it's called Walmart.
Oh, okay. I don't know.
No, hold on. But this is a different store though. They sell motorcycles.
Really?
Oh yeah,
In the store?
yeah.
Sounds like bikes.
I took a picture. If you go to lunch today, I'll show you. I took pictures of like the motorcycles inside the store.
Can you ride a motorcycle?
Well, I can definitely ride a motorcycle. I think I would have to get a bigger motorcycle that would be able to like really support my weight. I'm sure any motorcycle could like. I don't know. I mean, I know like Suzuki and some of that, so I didn't really look at the brand, so I'm not sure.
Are we,
I'm just trying to run the program.
yeah.
Is it crash or is it
Are we
running?
basically recreating what was on the other scripts from the other class?
Mhm.
So are we going to return?
Well, no, I'm not going to see anything. I should just see the hello world thing right now.
Yeah. No, I realize. I mean, what are we going to? So are we going to end up returning the?
We're going to displaying it.
Okay.
It's a weird noise. I wonder what that's all about. All right, we're just going to restart Android Studio. Yeah, you can haggle in Mexican Walmart.
Really?
Yeah. It's no price match guarantee either because every price is negotiable. Plus, you just have people in there that are trying to like resell you bananas and stuff. Like bananas are whatever, like 6 pesos, let's say. And that's the listed price. That's the listed Walmart price. But you might find a guy that's willing to sell it to you for 10 pesos. He gives you a banana, you walk out of the store, and he's gonna go hopefully pay for your banana. Otherwise, you just gave a dude money and robbed a Walmart. One of those two things happened. Yeah, right. It's a currency. It makes some sense.
Have you ever been to Vietnam?
I've not been to Vietnam. I want to go to Vietnam. See how big this update is. Is it nice how Android Studio, like ahead of like an update, they just say we're gonna make your ID just stop working. Look here. All right, we're gonna let that guy cook for a few minutes, and let's review in order, post order, that stuff. All right, so we talked about tree traversal, the different ways we can traverse the tree. I kind of left this pre-order, post-order thing out and said that's kind of databasey stuff. So I'll just kind of roll with that for right now. In order makes a lot of sense to us because this is more of a sorting thing, and one of the nice things for us about how a binary tree is functioning is that our as we add stuff, they're automatically being placed in the tree in an organized way. Okay, so if we look at in order, we're going to visit our left child first, then we're going to visit ourselves, then we're going to visit our right child. Pre-order, visit ourself, visit left, visit right. Post-order, visit left, visit right, visit ourself. All right, so for instance, if we're doing in order, on this tree, we visit left, then ourselves, then right. But remember, this is a recursive or a pseudo-recursive type of thing. So when I'm visiting this tree, so we'll update it to now we're visiting trees, right? It's a tree of trees. Mm-hmm. When I'm visiting this tree, in order, the first thing I do is I visit the left tree. So now this guy gets put on hold. Now I'm visiting this tree. When I'm visiting this tree, in order, the first thing I do is I visit the left tree. So I'm putting this call to visit in order on hold. I get to this tree. When I visit this tree in order, first thing I do is I try to visit the left tree. There isn't one. Then I visit myself. So I'll display 3 or return 3, whatever, however I'm implementing the in order thing. Then I attempt to visit the right tree. There isn't one. Bounce back up. Then I am able to bring back off the stack this call to visit in order. And that guy has now finished visiting his left tree. Now he can visit himself. 3. Then he tries to visit the right tree, doesn't have one. So now this call is finished, bounces back up. This guy now is popped off the stack, and we continue that run. So this guy has just finished his left tree traversal. He visits himself, 5. Then he visits his right tree. When we visit this tree in order, what do? The first thing we do is I visit our left tree. When I visit this tree in order, what's the first thing I do? I try to visit the left tree. Nothing there. Visit myself. That's the 6. Attempt to visit the right tree, nothing there. This call to visit an order is done. Bounce back up. This guy has now finished visiting his left tree, so he's going to visit himself. Then he attempts to visit his right tree. Nothing there. So this call to visit an order is done. Bounce back up. This call to visit an order is done. Now we visited the entire tree in order, and the order was 3, 3, 5, 6, 8. We pulled the stuff out of the tree in our case, numerical order. Oh, good. New project structure. That should confuse things.
Suggestions.
Oh, this is a Gradle. Oh, man. Major Gradle update. Gradle didn't work very well before, anyway.
You mentioned there were a couple other types of ways to traverse binary trees.
Pre-order and post-order?
Yeah, no, besides those, was there something about going to
Oh,
the
there's a
leaves?
depth first. There's a depth first and a breadth first search that that's not a way you would typically traverse a binary tree. It's a way you would traverse an n-ary tree.
Okay.
So effectively what we're trying to do is with n-ary trees, we're not limited to only having at most 2 children. We can have 9 child trees if you want. They're still trees though, so this idea of a tree of trees still follows through there. So with that in mind, we've lost that ability of self-sorting.
Okay.
So we might decide that we're going to store stuff. I mean, let's think about other uses for trees. You could use it for a hierarchy system for a company. Something like that, where this is the president. This might be vice president levels. Underneath this vice president, you have these people. That kind of stuff, right? Okay, so in a situation like that, you might do depth first because you might care about. You can almost treat this as a business vertical, and this is another business vertical. This is the VP of sales. This is the VP of research and development. Okay. Something like that. So everybody in this vertical, so if we're doing depth first, you're going to get all the stuff in that vertical collected together. As opposed to, and similarly, depth first over here, you'll get all these people collected together because you're going all the way down on this side before you bounce back up and traverse another side. Okay. Where breadth first will get all of the top level, all of your next level. So these are, in business, this might be called C-level people, CEOs, CFOs. Then maybe this is down to the VP level, that type of stuff. So you can kind of, depending on the type of data you're storing, it might make sense for you to pull data out of a tree in such a way that is pull data out of a tree in such a way that it's meaningful for the data you were storing. That makes some sense. But a lot of the stuff we're using trees for have to do with, a lot of the modern applications really have to do with GPS and stuff like that. That's more of what's called a graph data structure, but it's still a, non-linear linked data structure that kind of starts with the idea of a tree. All right, so working theory is this guy is all updated now. Let's see what happens. All right, we'll go with that dude. All right. I'm going to create a new emulator here. We're going to create a... Oh, that's bound to not work. So create another Pixel 2. I guess I'm going to stick with Oreo here. Let's see if we get some video. Ah! We got something. Something's cooking. It's fancier? Well, this is the Pixel 2 instead of the Pixel. Pixel 3 is even cooler. It's extra fancy. Box comes with crickets. Pixel 3 XL comes with a live Cobra in the box. All right, there we go. Oh man, I got this resource manager thing now. And then I'm going to go with, okay, here's this guy. So here's my main activity. All right, so let's uncomment my binary tree stuff and just make sure the app still runs. We're not going to see any output from it. All right, still runs. All right, so now let's go ahead and let's give ourselves an in-order traversal. Okay, so we're doing this inside of binary tree 2. So I'm going to write a public void. I'm going to say visit in order. I'm just going to write it pretty simply where I'll just have it print out what the payload is.
Okay.
I'll put some asterisks in front of it. That way we can find it quickly. And so we're going to say visit in order. So again, we have a collection of trees. So a binary tree is a tree of trees. We visit a tree in order. What does it mean to visit a tree in order? It means visit the left node, then visit yourself. Well, it means visit the left tree, then visit yourself, then visit the right tree. All right? So we're going to say, this is actually a... Let me see if I can show you a trick here. Well, let's write it outright first. So we're going to say if this dot left is not equal to null. If we have a left tree, this dot left dot visit in order. We'll visit it. Then we know we have a payload ourselves. Then if we have a right tree, we'll visit that in order. So that's all visit in order. If I have a left, visit it. Then visit myself. If I have a right, visit it. All right, so we'll go back here to main activity. And I'll go ahead and say bt.visit in order. We'll run this guy again. I'll bring up my logcat. And there we go. So sometimes you have those situations. It was showing my old dead emulator that I had closed. Hit these drop downs over here, and here's the one that's currently alive. Then it brought it up. So 33568 looks like my tree is being built correctly. So let's go back and look at binary tree 2. Isn't that a pretty easy data structure?
Yeah.
Huh? Like, why did it print twice?
No, it's just like I know it looks simple, but I was just still wondering like how's it print out like that? Because I'm still.
Oh, you're still processing it. Okay. Yeah. So this is me filling my tree. We're good there?
Yeah.
Okay, I got a tree with stuff in it. Now I want to prove that the stuff was stored in a reasonable order. Okay, and the easiest way to prove that to ourselves is we do a visit in order. Things should be sorted. All right. So when I go into binary tree 2 here, this is what visit in order says to do. That's the whole thing for visit in order. It says if I have a left tree, so if my left tree exists, I'll put this call to visit in order on hold. And I'll visit my left tree in order. So now I'm in my left tree, let's say. If he has a left tree, go back to our picture here. Right now I'm in my left tree. Does he have a left tree? He does. So I'll put this call to visit in order on hold. So I have 2 calls to visit in order currently paused. This one's paused and this one's paused. So then I visit this guy in order. So that is this call right here. Okay? Huh? First time through, it's the root node. That's the call I'm making. I'm visiting this guy in order. Then when I'm visiting him in order, the very first question I ask, does he have a left child? All right? That's the question I'm asking right there.
Okay.
Does this guy have a left child? Yes, he does. What do I do if he has a left child?
Like the left side.
I visit the left child,
So then
which pauses me.
Oh.
Okay, so this top level guy has to sit and wait for this guy to finish his visit in order. So he's being put on hold. He can't finish. He can't get to this line right here, my original root node. He can't get to that line where he visits himself and prints himself out until this call has completed. And that call is a blocking call. That call blocks, which means this guy has said, I'm going to visit my left child, so he's going to stop and wait. He's going to yell down to his left and say, visit in order, probably do in the kind of kingly voice with, pomp and circumstance, and visit in order. That's pretty good. Thought actually.
Pretty good.
That could be soundboard.
Yeah, that is soundboard.
The end thing, we have multiple screens.
53 minutes.
Funny, serious.
All right, so this guy is now waiting because the call to his left child visit in order blocks him. He can't continue on. He's got a wall here that is preventing him from finishing this line and getting to this line. And it's nothing special that we wrote. It's just that's how it works. Okay? When we make a call to a function, we only get past this line once that function call is completed. It just happens to be that function call is doing some other function calls, which is doing some other function calls, which is doing some other function calls. So we're kind of waiting there for a little bit, waiting for it to finally come back and finish. All right, so this guy is going to visit in order, which says he's going to check his left child. So he's going to visit him in order, which says he's going to visit his left child. He doesn't have a left child, so he doesn't get into this if statement. Instead, what does he do? He just prints out his payload. So the first payload that's going to print out here is this dude's payload. Then he checks his right child. There isn't one. So finally, this call completes. We bounce back up. Finally, that if statement, finally, this call to visit in order now completes. And this guy is able to visit himself. So he gets to this line right here.
So this sounds like a stack type of thing?
it's under the hood, it's implemented like a stack. That's why I was saying earlier in class, that's what we do in 470. We learn how to write recursion. Right now, we're experiencing recursion. This is the applied side of recursion, right? We learn how it's actually implemented under the hood in 470. All right, so back out here, I fill my tree, and I tell the tree to visit itself in order. Make sense? Okay, so what we're going to do for homework is we're going to have a screen in our app I'll put binary tree 2 next to it because that's what we're representing as our binary tree 2. All right, and this guy you don't have to color code it like this. I'm just showing you the pieces. All right, so he'll show his payload, and then he'll also have buttons for left and right. Yeah, this is all, this is what they teach in the multimedia design classes. It's all right colors go together where your eyes hit first.
Yeah, exactly. Because you look at the 5 and then you see
You see this
afterwards somehow.
You somehow keep yourself from throwing up. And then all right, so what we're going to have is we're going to, on top of our binary tree 2, we're going to give ourselves a visual way of traversing our tree. Okay, so when I click this left button, what's it going to do? It's going to take me to another screen just like this one. And that screen is going to show me the current state of that binary tree. So you're going to have an activity. So here's your hint. You're going to have a single activity in your app that displays the state of a single binary tree 2. Where a binary tree 2 is a payload and potentially a left and potentially a right tree. If I click the left or right, what does it do? It launches that exact same activity again, a new copy of it, but it's displaying the left or the right binary tree 2. Okay, so this actually is not going to be very difficult. What you'll have to do is figure out how do you pass the binary tree between the two screens and let them keep track of each other. Also pretty easy. Okay, so make sure you draw pictures. I expect this to feel very difficult for some of you. I expect some of you to be able to finish this in probably less than 30 minutes. Okay, so this is one of those assignments that's going to force you to think through that problem. And right now we're kind of swimming in those recursive-esque waters, which is uncomfortable for a lot of us. So it's okay if you're one of those that are going to find this pretty frustrating, but some of you are going to find this is a throwaway assignment. Go ahead.
For getting to the bottom of the binary tree, do you want to display null or?
You can just omit the button, but it doesn't matter. I mean, however you want to represent it is fine. I just want to be able to walk my tree. You know, something like that. It probably would be, actually, I won't even throw that in there. I was going to say it would be helpful to be able to go back up, but you already have that with Android with the back button. If I hit this left button and it takes me to my left subtree, and then I hit the back button on Android, it'll just take me up to one level. Okay. So it's built in. You don't have to write any logic. All right, questions about what I'm asking you to do? For our tree here,
For what you want me to do.
yeah, our tree here, Your first screen should show a 5.
No, I cannot imagine what you want.
I'm telling you.
No, on the screen, like.
This is payload. This is a button that leads to here. Let me draw one more tree.
Yeah, that might help me for another screen.
Remember, today is student, faculty, staff Bible study. Got in, grub. Go to the cafeteria, get a tray. Sign in, take it down to the terrace room.
Hang
You know
on,
how
I
much
think
longer
we
you
have
have to do it? You know how long? No, I meant to say, you know how long that took me? Oh my god. Like 4
Okay,
hours.
so what's going on with the tree?
All right, so
He's showing you what he wants it to do.
So, come on. I'm just making a shoe. You don't even fire. You can walk without your shoe being tied. I did that. I don't even walk without
that would be
It sucked. It actually
We have a
bothered me.
meeting, I guess not.
I didn't do that. Yeah.
Oh, you don't want my shoe equipment?
Yeah.
Your I-Core
I mean, it bothered me too, but I
certificate, Mary has it.
oh, thank you.
I was
3, 8.
Something
All right, so if I were to click this left button from here, it's going to show another screen that looks like this with 3 in payload. And let's make sure this guy has a, good, 3 in payload. But this guy does not have a right button because that 3 does not have a right child. So if I click left button from here, it's going to show me this tree. This tree is going to show me a 3, and it's going to have a left button to take me here, but it's not going to have a right button because there isn't another guy here.
So basically saying that you want me to know how to create like new activities when I click the button?
It's fun.
Yeah, we already know how to do that.
Especially the art lesson we're getting.
So like automatically.
If I click left,
automatically create it?
yeah, when I click left here, no, you already have a tree.
Visual.
A tree already exists. Just like we already have this tree with a bunch of stuff in it. I want you to be able to show that tree. So I'm just traversing it afterwards. Where if I'm here, I see that this guy has a left and a right child. If I click left,
Yeah, he's alive.
that's going to take me here.
Oh.
Okay, that's going to take me here. And this particular node, if we look back here, he has a left child, but he does not have a right child,
I think I just screwed my GitHub.
which is why he does not have a right button here. I have a left button I can click that would take me down to his left child, but I don't have a right button because he doesn't actually have a right child. There's nothing over here. From the 5, if I click the right button, it's going to take me to this node that has the 8.
Now it's I have 2 to push and 1 to pull down. Where?
And he also does not have a right child.
Did not exist under the floor class. I pull it off again and put it on here.
So do you see how these screens are identical to each
And
other?
I just pushed it once.
These screens have a payload and 0, 1, or 2 buttons. This guy has 2 buttons because he has a left and a right child. So if I click the left button, it's going to show the identical kind of screen, but a new copy of it. This copy will show that binary trees payload and his buttons for left and right. If I click the right button here, it'll show me this binary tree with his payload and his buttons for left and right. In this case, he only has a left child. If I were to click left here, it would take me to another screen that would show me the 6 with 0 buttons below.
Yeah, actually, I should probably go eat because I have.
Okay.
Make sense?
Okay, so basically you're saying that I need to, and you only give us a hint of like creating a new activity, so then I need to write a code that will automatically create a new activity?
You already have the activity. Your app is going to have exactly one activity in it.
Oh, okay, and then you function.
You're just showing that same activity multiple times with different payloads in it.
What? Oh, it's from my art class.
Make sense?
Yeah, and then I need to have a functions that like make the
No,
button
he
show up
messaged
or
me
like
while I was in my art
cut off.
class saying he couldn't get into Falcon then.
Oh.
So
because like if I create like a new activities and like